there are essentially two key components in our methodology. One is the reproducing kernel Hilbert space, which is a well-known tool in data analysis. And the other is operator theory, which is a tool that's been prevalent in quantum mathematics for a very long time and is very popular. So I'm going to give my talk on my topic of PhD research, that is a functional operator for uncertainty quantification in the RKHS. So the objective of my work is pretty straightforward. I develop a framework for accurate and multi-moment description of uncertainty of data and learning models. And this is specifically based on their density characteristics. So for example, take a toy example in data uncertainty. If you have a sine wave, then we know that the highest density points occur at the peaks of the sine wave, and anything away from it, you should get high uncertainty. So if you look at the PDF characteristics of a sine wave, it's characterized by two peaks that determine the two troughs of the two peaks of the sine wave. And what we want to do is basically come up with a framework that is able to efficiently separate out different regions of this signal based on the density characteristics. So the shaded regions are the high uncertainty regions, and the non-shaded regions are the low uncertainty regions where the density is very high. And similarly, for model uncertainty, you can visualize any neural network trained on some specific training data pairs. The uncertainty envelope associated with that model should characterize high confidence in regions around those training data pairs, and that uncertainty should increase as you move away from those training data pairs. And if your framework is efficient, it should even be able to spot regions in between the training data pairs that may or may not be inside the pattern that a model is trying to learn. So this is the goal of my framework, and although it's conceptually easy to understand, it's surprisingly very challenging to implement, and it's a very hot topic in current ML research. So such a framework can have a lot of applications. One is model uncertainty quantifications that I briefly discussed. The other is time series analysis, specifically clustering and anomaly detection, because you can use an uncertainty framework to identify different regions of the time series. Dependency and similarity measures can also be incorporated using such a framework. And the other thing is you can come up with a very good characterization of surprise and novelty using such a framework. So there are essentially two key components in our methodology. One is the reproducing kernel Hilbert space, which is a well-known tool in data analysis. And the other is operator theory, which is a tool that's been prevalent in quantum mathematics for a very long time and is very popular. So the reproducing kernel Hilbert space basically provides a very mathematically rigorous functional representation of nonlinear patterns in an input data without having to explicitly know those patterns. And according to Moore-Arrowsand theorem, if you have it is constructed using a symmetric non-negative kernel function K that operates on the inner product of the input space and maps it to a real number. And the representer and linear combinations in the RKHS can be used to build nonlinear deterministic functions, and it helps bypass the need for highly iterative training procedures in learning algorithms. And also the representers theorem assures that the computations in the RKHS directly map to the input space. So the operator theory on the other side is a tool in quantum mathematics and specifically in quantum physics that to provide an accurate description of the local dynamics and anisotropy of particles in a field. And it is known to provide multi-scale description of uncertainty in quantum physics in terms of multiple local moments of any particle that is operating in a field. And a very elegant aspect of quantum theory is that most of the operators operate in the Hilbert space. So any system that you're defining in physics can be are typically defined in a Hilbert space, in a finite Hilbert space, and operator theories are typically implemented on those spaces. And the reason I highlight the last 2 points of the key components is that this aspect provides a very good way to link RKHS in data analysis with quantum theory and in quantum physics and mathematics. So we can essentially use operator theory in the RKHS to use all the advantages of that operator theory provides in physics, but in data analysis. And this is the inspiration for coming up with a physics-inspired framework for model uncertainty quantification. So the overall, so the overview of the framework is as follows. You have any input space data. It could be a time series, it could be a set of images, or it could be the weights of a trained neural network. And what we do essentially is first project that data into an RKHS field defined by psi x, and this is usually used for quantifying the PDF of the data. And the second step is to use physics-inspired operators, which I'll get to in a moment, what these are, but these are basically Laplacian-based operators that quantify the gradient flow of the PDF that is characterized by the RKHS. So essentially, you implement some Laplacian-based operators on psi x to get the gradient flow of psi x, and this helps you characterize the density of the input training data in a very high resolution manner. And this is depicted by this uncertainty landscape figure that I show here. What you basically get implementing both of these is a potential field that is characterized by different moments of uncertainty, and it's a continuous space. So at any point in this space, you can characterize the uncertainty associated with that point by simply looking at the values of the moments in those space. For example, if my point y is here, then the uncertainty characterized around y can be obtained by looking at the moments in the neighborhood of y. So this is the basic idea of the framework. So I define my problem setup as follows. Let's suppose that we have a given trained neural network, with a regular training data, xi, yi. A training input is defined by x, desired output by y. X can be a d-dimensional real number, and y can be any one of k labels. So it can be a k-class classification problem. Test input is defined by x star, and test output is defined by y star similarly. And our goal is to come up with an uncertainty envelope for a given trained neural network that behaves in this manner. So you have training data pairs, and the model should logically be very confident around those training data pairs and lose their confidence or have high uncertainty when it goes outside of those training data pairs. So essentially what we want to do is characterize the predictive PDF of a trained model that is given by this formulation. And we want to evaluate that predictive PDF on any test output given an input and trained weights W. And to make it more challenging, we also incorporate covariate shift during testing. So in this case, a test set governing, so what covariate shift means is that, the test set governing PDF has undergone a distributional shift that makes it no longer equal to the training set PDF, to the governing PDF of in the training input data. And this happens while the target conditional distribution remains the same. That is, the Py of x remains always the same in both test and train. So this is the basic definition of covariate shift, and this gives us is a very common problem in modern applications. And uncertainty frameworks, it is a good way to judge uncertainty frameworks, because you can judge them by their ability to detect these covariate shifts during testing. So the typical methodology for model uncertainty has always been the Bayesian methodology. And that involves an inference problem where you have to estimate the probability of weights given a training data set. And this involves a huge marginalization problem, which is terribly expensive to compute. So, and that's why Bayesian neural networks have really not come to the forefront, because of this problem. So the posterior predictive PDF is basically a marginalization problem over the weights. And recently there has been a lot of push to come up with approximate methods of implementing Bayesian neural networks, and some of those methods are as follows: the fast variational inference, Monte Carlo dropout, ensemble methods, and approximate Bayesian methods. So all of these try to approximate the posterior PDF using this formulation, but try to do it in a very approximate manner, so that you don't have to compute the entire integral here. Specifically, approximate Bayesian methods have been very popular in the recent years. Many top conference papers are coming out from the last category of methods. So our interpretation of model uncertainty is very different from the Bayesian approach. The Bayesian approach, as I discussed, is a marginalization problem. In our approach, given a trained neural network, we come up with an initial approximation of the predictive PDF. And we do that by projecting the weights, the trained weights of the neural network into an RKHS. And the goal of doing this is to approximate the intrinsic probability distribution function of the weights in the most efficient way possible. So this is the first step. And if you evaluate this PDF at any given model output, you get a sense of how the weights behave around that particular output. And the second step is to use operator theory in quantum mathematics to measure the gradient flow of this RKHS projection of weights, or the PDF of the weights. And that gives us the variability of the PDF of weights around the local neighborhood of the output. And this can be visualized in terms of Bayesian method similar to regularization, that which kind of does the same thing, but it does not go as local as our method does. Is basically quantify how much your weight PDF varies around a given output of the model. So that principle remains the same in our framework, but we do it in a more efficient manner, and we come up with a multimodal description of this local variability of weight PDF around a model output. So this particular metric that we use for quantifying the PDF of the weights in the RKHS is called the information potential field, and it is defined as follows: given a non-empty input set X, representing an input random variable, and a symmetric non-negative definite kernel function K that maps from the inner product space of X to a real number. The information potential field is an estimator of the PDF of X that is simply formulated as the empirical mean of kernel evaluations at each point in the input space. So it's a simple formulation in the RKHS. And if we employ this for our method for quantifying the weight PDF, the formulation becomes as follows. We project the information potential field of weights is determined as the mean value of kernel evaluations centered on each of the weights of the model. And this is the intrinsic PDF of the weights that we work on. And specific.
Rishabh, may I interrupt the thing here? Sure. You call the weighted information potential field. So T is from 1 to n. So n is the number of parameters in the neural networks.
Yes, n is the number of parameters.
And
in
the
neural network.
WT is one of the, for example, one of the edge connect the weight in the neural networks. So
yes.
So
yes.
which means that the n should be very, very large if it's
theoretically it is large, but as I come to the experiments, I'll show you that we do not use all of the weights in the neural network. We do average pooling of weights, and that significantly reduces the effective value of n here.
I see.
So it is computationally very fast. I can show you the
okay, thanks. Okay.
Yeah, sure. So this is the weight PDF defined by the information potential field constructed by model weights, or the effective model weights that we use. And if we evaluate it at any model output, we get an initial approximation of the predictive PDF of the model. And this information potential field has some very good properties. It is basically as you might have noticed, it is the Parsons window estimate of the PDF in the RKHS. So it is an asymptotically unbiased PDF estimator, making it a very good metric for our use. Another interesting aspect of the information potential field, or the IPF, is that it has a wave interpretation. That is, it has a physical interpretation as a wave function. Because you can visualize the IPF as a group of Gaussians centered at samples, you can typically visualize this as a field centered at each sample. Much similar to, say, the gravitational field created by a set of planets. But instead of the gravitational force of attraction, here the interactions between Gaussian particles is governed by the kernel, which is the Gaussian kernel that we use in our case. So and this field is an equivalent of a probability measure in the RKHS. That is, it gives us the probability at each point in the space that is induced completely by data. So this is a very interesting aspect of the IPF that helps us to incorporate quantum physics operators into it to quantify model uncertainty. Another association is the kernel mean embedding. The information potential field is also the empirical approximation of the kernel mean embedding, which is a very well-established theory of using the reproducing kernel Hilbert space to characterize probability distributions. It has some very good properties, such as it is a universal estimator of data PDF, and it is injective for characteristic kernels. That is, if the approximated PDF means using the kernel mean embedding are equal only if the distributions are exactly the same. So now coming back to our framework, this is the physical interpretation of our model uncertainty framework. We have a trained neural network. We take the RKHS embedding that quantifies the PDF of the weights. We implement some gradient flow operators from quantum physics on this field that eventually leads to these uncertainty moments, forming a continuous uncertainty envelope at any point in the space. So when we evaluate the RKHS embedding upon which the gradient flow operators operate at any point in the output space of the model, we get an associated output local uncertainty moments around that output. So this is the basic framework. So now, so I have discussed how to characterize the PDF of the weights and use that. But now the second thing that I'm going to discuss, the second aspect of our framework, that is how to come up with an efficient formulation of the gradient flow of the PDF of the weights. So here, the proposal is to construct a Schrodinger's equation to describe this gradient flow of weights. And Schrodinger's equation is basically an equation that is very well established in quantum mathematics that uses a set of operators on a stochastic system to determine its dynamics. So the stochastic system is determined by the wave function psi x that in quantum physics may describe the probability measure of a particle in a field. And h here is the Hamiltonian that measures the rate of change of that wave function or the particle in the field, while preserving the total energy. So h is simply a set of operators that gives you a good estimate of the rate of change of the stochastic system. And when you operate that on the wave function, what you eventually get is a set of eigenfunctions over the stochastic system psi x that basically defines the uncertainty or energy levels of the system in terms of many different moments. So you see here that Schrodinger's equation can be a very good tool to describe multimodal multi-moment uncertainty of a given stochastic system. So a very good example of this is the quantum harmonic oscillator. So if you have a particle attached to a spring, it moves in a certain way, and A and B here is a simple Newton's description of how that particle would behave, in space and time. But if you incorporate quantum mathematics into it, if you approximate the motion of this particle using a Schrodinger's equation, then you get the description of the dynamics of this particle in terms of many various moments, as you can see, from C, D, E, F, and GH. Each of these describe specific moments of that particle, and you can see that they have a very unique way of characterizing the particle at each point in space. So our goal is to essentially, so this is our inspiration for developing an uncertainty framework for models, is that we want to construct a Schrodinger's equation, similar to a quantum harmonic oscillator, but for models. And the IPF provides a very good way of doing that, because we can directly, replace this wave function by the IPF of the weights, and come up with similar uncertainty moments, similar to this quantum harmonic oscillator that you see. So the specific equation of a harmonic oscillator in this case, the Hamiltonian H is a set of two operators. That is, one is the kinetic energy operator and the other is the potential energy operator. And once you solve this equation, you get a set of modes of the stochastic system, that is the probability of the particle. And so this is what we want to do in the case of models. So we now move from the information potential field to a new concept called the quantum information potential field, where we construct a physical system governed by the weight PDF. So here, the weight PDF psi of W is used to construct a Schrodinger's equation, associated with a given Hamiltonian and a given energy value. And our goal is to solve this equation and extract various uncertainty moments of psi W, which is the PDF of the weights, essentially. And using that solution, we can get various moments of uncertainty of psi W. So how do we do this? We have the information potential field of weights, and here we construct the Hamiltonian as in terms of a potential energy operator and a gradient flow operator, which is the main aspect that quantifies the gradient flow of the IPF. So the gradient flow operator basically consists of a Laplacian operator that is slightly scaled by the kernel width that we use in the RKHS. And once we construct this Schrodinger's equation using this method, we derive a new term called, through the evaluation of the potential energy operator, and this is called the quantum information potential field, which now describes the dynamics of the PDF of model weights in terms of its gradient flow. And you can see that, this equation is naturally normalized with itself and scaled by the kernel width, and also characterized by an energy function that is EW. I did not randomly come up with these operators. There is a specific way of, coming up with this description of the dynamics of the weights, or the PDF of any stochastic system, and that is essentially called the perturbation theory. So what perturbation theory does is, perturbation theory is a very well established concept in quantum mathematics that is used to solve any given Schrodinger's equation that we don't know much about. So what we do in perturbation theory is that we, let us say we want to solve this equation. We start with an approximate solution to this equation given by psi of 0. And we introduce a perturbation Hamiltonian called H of P. So what we are essentially doing is disturbing the system just a little bit and observing its dynamics. So once we do that, we directly obtain the solutions over psi of x in terms of a power series expansion. And this is the concept that we use for solving our Schrodinger's equation over the model weights. We want to solve this equation. So we come up with a perturbation Hamiltonian that is described by the Laplacian, scaled by the kernel width, and we introduce that to the Schrodinger's equation of model weights. And essentially we come up, we arrive at this formulation, that is the quantum information potential field, that describes the local dynamics of the IPF around a given model output. And so this is a very good description of the local behavior of model weight PDF around a given model output. So I won't go into the details of perturbation theory, but this is the abstract description of how we use it. So another aspect of perturbation theory, as you have seen, is that once you describe a system and try to solve it using perturbation theory and introduce a perturbation Hamiltonian, what you arrive is a power series expansion of the wave function that you are solving for. So in this case, essentially, we come up with a quantum information potential field, but we also come up with a modal decomposition of the wave function associated with that QIPF. And this is the power series expansion. So we can in fact modify this QIPF formulation in terms of the modal decomposition. So H naught is decomposed into H naught K, that is H naught 0, H naught 1, H naught 2. Each of these are the QIPF uncertainty moments that are evaluated at any particular model prediction Y naught, Y star. So for our case, for approximating this power series, we simply use the IPF as our initial solution, and then we project this IPF into orthogonal Hermite polynomial spaces. And that basically gives you the various moments of the QIPF, and these moments act as the uncertainty moments that you want for the model. So essentially, our framework consists of three very simple back-to-back formulations. First, we quantify the weight PDF in the Gaussian RKHS using the IPF, and we can evaluate that at any output point of the model. And that gives you the predictive PDF of the model, an approximate initial solution of the predictive PDF of the model at any output point Y star. Then we use the Schrodinger's equation. We use the Laplacian operators to come up with the QIPF of the weight PDF that basically describes the local variability of the IPF around a model prediction. And using perturbation theory, we can actually further decompose this QIPF of weight PDF into various orthogonal moments. And these are basically the moments that quantify the uncertainty at any particular output of the model. So in this given illustration, this has nothing to do with a trained model. This is a simple sine wave, and we evaluate what the uncertainty moments look like for this particular sine wave. And as you can see, the IPF quantifies the PDF of the sine wave, which as expected looks like a bimodal distribution. And the colored solid, the lines are what the QIPF modes are. And you can observe that mode 1 quantifies regions quite near to the peak where the density of sine wave samples are the highest. And as you go outside towards the tail regions of the sine wave, you have higher order modes popping up. So you have mode 1, mode 2, mode 3, mode 4, mode 5, and like that. It keeps on going. And even at the mean value of the sine wave, that is at 0.0, where uncertainty should be slightly higher than that of the peaks of the sine wave, but still lower than the tail regions. And that you can see here that for a very brief moment in the mean, mode number 2 dominates over mode number 1, indicating that there is slightly higher uncertainty at the mean. So this is just a very brief illustration of what our basic illustration of what our framework does in the space of data. So coming back to model uncertainty, this is how again our framework looks like. We and now we have defined gradient flow operators from quantum physics that operate on the QIPF of the weights and come up with the output local uncertainty moments. And this is basically given by this definition, which I won't go through. I just described it. You have a trained neural network with D. You have an IPF defined by psi, and finally, using these, you come up with the QIPF formulation that is given by this equation here, where psi of k is the kth order Hermite function projection of the information potential field. And this is the Laplacian operator. So this is our final formula. So to summarize, what is the difference between what is the advantage? What do we gain by doing this? That is what I express here. Bayesian methodology for uncertainty quantification involves multiple iterations of the model. And there are various ways of doing this. You can do it using Monte Carlo dropout or ensemble approaches. So because of this, it is very computationally expensive to achieve optimal solutions from the perspective of Bayesian methodologies. And if you want to use approximate Bayesian methods, it leads to very poor approximation of the posterior, and especially in the case of high-dimensional problems. And we are able to, using our QIPF approach, overcome all of these drawbacks of Bayesian approaches. First of all, it is a single-shot estimation of model uncertainty. That is, you do not need any iterative procedures. It is a functional method. You have deterministic functions that describe uncertainty of the model at each point in the output space. And because of the multi-moment nature of this framework, it is able to provide very precise uncertainty estimation. It is significantly simpler to compute because you are not going over multiple iterations. And we are also not using all of the weights that Sujian very correctly had pointed out earlier in the presentation. That despite that formulation, we do not actually use all of the weights. We do some average pooling of weights, and we use so the number of effective weights is very less. It is also non-intrusive to model training. You can use this directly on point prediction neural networks that have already been trained. And because of the utility of Gaussian RKHS, it is a very good functional estimator of the model PDF. So to give you another way of differentiating this from the Bayesian viewpoint is that you can visualize the Bayesian method of quantifying uncertainty as involving iterative procedures that quantify variability of the output with respect to the weights. So in this particular example, you drop certain weights and evaluate how the model output varies in the output space around a particular output. This is basically what Monte Carlo dropout does. But essentially, all of the Bayesian methods, implicitly do the same thing. Drop weights and take multiple iterations of the model and come up with and quantify the variability of the results that quantifies the model uncertainty. But our approach does quantifies model uncertainty in a very different manner. The intrinsic variability of weights is functionally defined in our case, and so we do not need any iterative procedure. We have a map of the model weights in an uncertainty landscape, and what we are doing is simply varying the model output instead of messing around with the model weights. We just vary the model output in its local neighborhood to see how those functional moments change. So if there's a high variability in those functional moments, QIPF moments, the model uncertainty is very high. And if it's not, then the model uncertainty is low. So we are essentially looking at in the reverse direction, that is, change the output to quantify its uncertainty instead of changing the weights. So now coming to some results, we start with some illustration of regression examples. So in this case, we trained a small 3 hidden layer neural network on 120 regression points. So it's a highly over-parameterized network that we are, that is overfitted onto a very few number of samples. As an extreme case example. So here the training samples are represented by the red dots, and the pink regions, denote regions in the data space where the model has not undergone any training. So you see here that the QIPF is able to discriminate those regions in terms of uncertainty very well from the training regions. That is, it shows high uncertainty where the training samples are not present, and that uncertainty increases as you move away from the training region. Other methods also like SGD iterates and stochastic weight averaging using Gaussian method, which is another top approximate Bayesian method that is used. You can see that those methodologies also try to do the same thing, but they are simply not as effective as QIPF because SGD, you can see, does not extrapolate well outside of the training data. SWAG method does not recognize the small untrained gap here, although it extrapolates well. And MC dropout has the same problem. Furthermore, you have to take various iterations of the model, and you come up with these stochastic iterations that really do not give you any meaningful information of the uncertainty. All you have is the mean and the standard deviation of the uncertainty characterized by these methods. And so this is just the second moment information that you're obtaining from these methods. But in the case of QIPF, you can see that the uncertainty is not only defined by mean and standard deviation, but each of the modes of the QIPF. So you can see that the highest order mode, that is mode number 3, is the most sensitive when it comes to when you move outside of the data regions, and that sensitivity decreases. So the higher order modes are more sensitive, as you can observe from this figure. And there is a very systematic way in which our framework quantifies uncertainty. That is, the highest order mode is the most sensitive, second highest is the second most sensitive, and so on. So this really gives you a meaningful multi-moment description of uncertainty that is not possible to obtain from other methods. And you can also see that it's much more precise and sensitive. And similarly, for in the case of classification example, we just used a 2 moons dataset corrupted by some noise, and you can see that using different, you can see the QIPF method, quantifies uncertainty very well in the decision boundary. It shows high uncertainty at the decision boundary. It becomes confident only on the thin regions or the patterns represent where the training samples are present. And as you go outside of the training samples, the uncertainty keeps on increasing. Monte Carlo dropout, on the other hand, although it detects the decision boundary very well, it does not show the same uncertainty. It becomes more confident as you go outside of the training data, which is very unrealistic. The stochastic gradient descent iteration method improves upon Monte Carlo dropout, although it does not have the same high resolution of the decision boundary. It at least recognizes that as you go outside of the training region, you're supposed to become more uncertain in your predictions. And similarly, the SWA Gaussian method improves over the SGD iterates. This is an approximate Bayesian method, and you can see that it provides slightly better results. But QIPF, but even here, it fails to detect the decision boundary very well. So QIPF is able to do both of those things, detect the decision boundary and show high uncertainty as you go outside of the data set. So another sanity check to actually see if our method is detecting the bias variance trade-off of the model very well. We use the same regression example, but we use different regularization parameters. So for example, in A, there was no regularization. In B, there is some regularization provided. So you can see that the uncertainty outside of the training data set reduces a little at the cost of bias inside the training regions. That is, the uncertainty increases in the training regions. And this trend continues on as you increase the regularization. For maximum regularization, the QIPF assumes that the model is equally confident everywhere. And this makes sense because that is what regularization does, right? It changes the bias variance trade-off, and that is correctly reflected by the QIPF. So this just tells you that, the QIPF is essentially a feasible tool to accurately measure the predictive PDF of a model. So now coming on to the main results, what we do here is, what we are very interested in is, detecting in classification examples when a model has made wrong predictions, right? Any uncertainty framework should be able to recognize that. So in this example, we have a simple LeNet model trained on KMNIST data, and we characterize this ability to separate distributions of correct and wrong predictions of the different uncertainty methods. And we do this using the histogram of uncertainty values of correct and wrong predictions. So the histogram of correct predictions is denoted by the blue histogram, and the histogram of the uncertainty estimates associated with the wrong predictions is denoted by this red histogram, as you can see. And you can see that from as compared to many different methods, as Monte Carlo dropout and stochastic variational inference, the QIPF is able to separate out the wrong predictions much more efficiently from the correct predictions as compared to other methods. And this is also reflected in the ROC curves of wrong model prediction detection of the different methods. You can see that QIPF achieves the highest ROC AUC and the precision recall characteristics compared to all of the other methods. So now, as discussed earlier, we are also interested in comparing different uncertainty quantification methods under a situation where your test set undergoes a distributional shift. So in this case, we take some simple corruption techniques and we increase the corruption intensity. For example, if in the case of rotation at each intensity level, the digit undergoes a different intensity of rotation and different intensity of shear or zoom or shift, So, and what we do is basically compute the ROC AUC at each of these intensity values. The average ROC AUC, that is area under the curve of ROC AUC and precision recall curves for each of these intensity levels. And we see that the QI from these graphs, this is the example of rotation corruption. We can see that the QIPF almost consistently remains higher than all of the other methods, both in the case of ROC AUC and in the case of precision recall AUC. As we increase the rotation angle, the error detection PR AUC remains higher for QIPF as compared to other methods. And similarly, this example shows for shift corruption, QIPF still performs better than all of the other methods. And calibration is also very important in when it comes to judging uncertainty quantification measures. That is, you want to make sure that the more wrong predictions you get from a particular set of test samples, your uncertainty over that entire set should increase accordingly. That is, it should not drastically increase, but it should increase proportional to the number of wrong examples that the model is predicting, right? So, so there are some methods to do that. One is the expected calibration error, and the other is error point biserial correlation. So you can, the expected calibration error, the lower values, the better, and you can see that the QIPF is much more calibrated than most of the other methods, except maybe the ensemble method a little bit, but it still outperforms the ensemble in many cases. And the next curve shows you the point, basically the correlation of the uncertainty estimates of the different methods with respect to the prediction errors of the model. And you can see that that correlation is also very high for QIPF as compared to other methods. So to summarize, this table gives you the average ROC AUC and PR AUC values for each of the different methods for many different data sets. That is MNIST, KMNIST, CIFAR-10, CIFAR-10 trained using BGG3 and also by ResNet 18 network, and for many different corruption types. And you can see that in most of those cases, the QIPF has the highest ROC AUC and PR AUC, followed by the ensemble method, which is also known to perform very well under these situations. And similarly, for the expected calibration error and Brier score, these are calibration metrics for comparing uncertainty estimates, and the lower values, the better. And you can see that QIPF is approximately, it's always in the top two. SVI does very well when it comes to, that is stochastic variational inference, does very well when it comes to calibration, but QIPF also is able to match that. And so that basically summarizes the results on covariate shifted test data, how different uncertainty estimates behave in that scenario. And regarding the computational complexity, so there are just two factors that contribute to the computation complexity of the QIPF. That is the number of weights for the computation of the IPF and the number of extracted uncertainty moments. Now, and since we are doing average pooling, we do not use all of the weights of a neural network, which would otherwise be very computationally intensive. But we do average pooling, and we effectively reduce the value of n to a very low value that makes the algorithm very fast without sacrificing the accuracy. So all of these results that I've shown you are over average pooled weight values. So I'm not using all of the weights in these examples. And you can see that the QIPF for different models, the computational time per test sample is always very low of QIPF compared to other methods like MC dropout, and it scales very well as you go to bigger networks. So yeah, that basically concludes my my framework. And there are some other aspects that we are also working on. We want to see how such an uncertainty framework would be, given its high sensitivity and specificity, would be able to do in adversarial attack detection and generation. We also are interested in implementing it directly on data in time series to quantify dependency and similarity measures. And we are also working on, seeing if, such a framework provides a very accurate description of how a neural network learns. So basically, to quantify the training dynamics of a neural network, can we use this framework or not? So these are some aspects that we are, exploring. And of course, like any other algorithm, there are some disadvantages. Of course, I left out that slide for some reason. But the disadvantage of this framework is that you have a hyperparameter associated with it. That is the kernel width and the number of modes. So you have to have some kind of validation to know what the correct value of the kernel width, that is sigma, should be, and how many modes you need. So these two are really hyperparameters, and this can change depending on the nature of the data set or nature of the trained model. So there is some validation required to come up with the appropriate values. And we are currently working on, automating this procedure. But as of now, that is one drawback of this framework. And so these are just some references. If you a detailed description of what I presented is available in this archive that is currently under review, a functional operator for model uncertainty quantification in the RKHS. The other published work related to this are these two works that you can always refer, and you can always contact me. I'm always open to collaborations, and I'm always looking forward to working with different labs and different groups to come up with new ideas. And thank you.